class 12. In this video we are going to discuss the topic photoelectric effect. But before we actually jump into the topic, let us give a brief look at the history and the chronology of the events. See, in 1672, Newton actually had given his corpuscular theory, something called corpuscular theory, wherein Newton had considered light to be made up of particles. Newton had already given that. But in 1678, Dutch physicist Christian Huygens, he proposed his wave theory. We've learnt about Huygens' wave theory, which was initially used to prove reflection diffraction of light. We've seen the proof of reflection and refraction also using Huygens' principle. Now, because of, and in 1801, Thomas Young, he proved the interference of light using wave theory of light. So since, these different phenomena like interference, also diffraction around 1816 or 1818, in between 1816 and 1818, French physicist, I forgot to write his name here, his name is Fresnel, A.J. Fresnel, F-R-E-S-N-E-L. A.J. Fresnel, a French physicist, he explained diffraction using wave theory of light. So you could see that, around the 19th century, different phenomena like interference, diffraction, and before that, reflection, refraction, phenomena like reflection, diffraction were being proven using wave theory of light. So therefore, Newton's corpuscular theory, it was not accepted since these different phenomena were being proven using wave theory of light. Now what happens is, in 1898, J.J. Thomson, he established that when light falls on metal surfaces, and in fact what kind of a light it should be light having short wavelength or a high frequency. So if light having short wavelength, which means light having high frequency, falls on metal surfaces, the metal surface, it starts emitting electrons. Okay, and this phenomenon is what is called photoelectric effect. And it was not just J.J. Thomson who worked on photoelectric effect. In between 1886 and 1902, German physicists Heinrich Hertz and Philipp Leonard, both of them German, they independently performed many experiments on photoelectric effect. But still, they were performing many experiments based on photoelectric effect. They were looking at different observations. They were getting different observations. But still, photoelectric effect could not be proven. Okay, photoelectric effect, we will see later on in this video also that it could not be proven using wave theory of light. Now, in 1900, what happened is Max Planck, German physicist Max Planck, he gave his quantum theory of light. Okay, in quantum theory, what happens in quantum theory of light? In quantum theory of light, Max Planck, he proposed that, light travels in the form of definite packets of energy, definite packets or quantum of energy, and these definite packets or quantum of energy are what are called photons. Now each photon, Max Planck said, carries an energy equal to h nu, Greek letter nu, where nu is the frequency of light and h is something called Planck's constant. And Planck's constant has value 6.626 into 10 to the power minus 34 joule second. Joule second is the unit. Okay, you can take it to be 6.6 into 10 to the power minus 34 joule second. So in 1900, Max Planck, he gave his quantum theory of light to, prove something called black body radiation. Now there's a phenomenon called black body radiation. In order to prove this black body radiation, which also again could not be proven using wave theory of light, Max Planck gave his quantum theory, wherein he said that light travels in the form of definite packets of energy called photons. So basically light is a particle, what Max Planck said is. And using that theory, using this theory, quantum theory, Max Planck proved black body radiation. Now we need not go into the details of black body radiation since it's not there in the syllabus. But please do remember, black body radiation, so to say, proves that light is a particle. And for this quantum theory, Max Planck also won the Nobel Prize in 1918. Just a GK for you all. Now what happened is, in 1905, Albert Einstein, the famous physicist, of course, he explained photoelectric effect using quantum theory of light given by Max Planck. Albert Einstein explained photoelectric effect in 1905 using quantum theory of light, and for which again Albert Einstein won the Nobel Prize in 1921. So it is Albert Einstein who explained the photoelectric effect eventually, remember, in 1905. Many people were working, like Henrik Hertz, Philip Leonard, J.J. Thomson, they were working on photoelectric effect, but they could not prove the photoelectric effect. So Einstein is the one who used quantum theory of light to prove photoelectric effect, remember. Okay, now let us look at the different observations of, the different experiments performed especially by Henrik Hertz and Philip Leonard. So basically what you have is, you have a discharge tube. Discharge tube is basically a tube made up of glass. Your tube light is also a discharge tube, so to say. So we have this discharge tube. Inside this discharge tube there is no air. It is, so to say, there's, all the air is pumped out. So you have almost a vacuum like situation or scenario inside this discharge tube. And you have this window over here from where light can enter. Light can come and strike the metal plates over here. So this is a metal plate P1 which is connected to a negative terminal, and this is another plate P2 which is connected to a positive terminal. So when light is made incident on this negative plate, or so to say the cathode, this metal plate, what happens is, what is seen is electrons, they get emitted. And these electrons that get emitted when light is made incident on a metallic plate, these electrons are called photoelectrons. Now these photoelectrons, which are negatively charged, of course, they are attracted by this positively charged plate. You can see it is connected to the positive terminal. So therefore these electrons are attracted towards the positive plate, and thereby what happens is there is a current flowing in this circuit. And this current is what is called photocurrent, remember. So these electrons coming out due to light or photons being incident on the metal are called photoelectrons, and the current flowing is what is called photocurrent. Now let us discuss the different observations as seen by Hertz and Leonard in their photoelectric effect experiment. Now you can take a notebook, a pen, okay, and you can start writing down the important points, whatever you feel important, and these graphs and the graphs also. Alright, so it was seen that, for a given intensity of light being incident on the metallic plate P1, and for a given frequency and intensity of light being incident on plate P1, on increasing the positive potential of this P2, so you increase the positive potential of P2, what happens is the photocurrent did not increase. It was seen that there is no increase in photocurrent, as you can see it over here. So for a given intensity and frequency of light being incident on the metallic plate P1, on increasing the positive potential of P2, the photocurrent did not increase. Why? Because for a given intensity and frequency of light being incident on the metallic plate, certain number of electrons are being emitted. Okay, and whatever number of electrons are emitted, they are already reaching the positive plate P2. And when you go on increasing the potential of P2, there are no further electrons left that are yet to reach P2. So whatever electrons are being emitted, they are already reaching P2, So when we increase the positive potential of P2, then we don't have any further amount of electrons that are to reach P2. So to say, the number of electrons being emitted from the plate is not dependent on the potential difference. So we go on increasing the positive potential of P2, we cannot go on further increasing the number of electrons coming out of the metallic plate, remember. So that was the first observation. Now what was observed next is the photocurrent, or the rate of emission of photoelectrons, meaning the total number of photoelectrons coming out of the metallic plate, is directly proportional to the intensity of incident light. So on increasing the positive potential, the number of electrons coming out of the metallic plate did not increase. So to say, the photocurrent did not increase. But on increasing the intensity of light, keeping the frequency fixed, but on increasing the intensity of light, it was seen that the number of photoelectrons coming out of the metallic plate also increased. And in fact, the number of photoelectrons coming out of the metallic plate was directly proportional to the intensity of incident light. So therefore, when we plot a graph of photocurrent or number of electrons to the intensity of light, you get a straight line, directly proportional graph. So this is one important observation. So you can make a note of all these things, remember. The other thing, then after, see, on increasing the positive potential of P2, there was no increase in photocurrent. So what we now do is, we start making P2 negative with respect to plate P1. So to say, it's like we change the polarity. So this plate is now connected to the negative side and this plate is connected to the positive side. It's like that. Okay, so P1 is connected to the positive terminal of the battery. P2 is connected to the negative terminal. So P2 is negative with respect to P1, or relative to P1, P2 is negative at a negative potential. So if P2 is given a negative potential, what is seen is that the current immediately decreases. But still, though it decreases, it does not become zero. Okay, so when we make P2 negative, so this is like the negative plate now, this is like the positive plate now. So when P2 is negative with respect to P1, what happens is the number of photoelectrons reaching the plate P2 decreases. Because obviously this is negative, electrons are negatively charged. So what happens is they should repel each other. So the number of electrons reaching P2 decreases when P2 is made negative, but still it does not become zero. So what can we conclude from this? What we can conclude is that the electrons coming out of the metallic plate, of course, they possess kinetic energy. Since they are moving from plate P1 to plate P2, obviously they should be possessing kinetic energy. That is obvious. But the other thing is, the electrons coming out of the metallic plate P1, they do not carry the same amount of kinetic energy. All of the electrons coming out of the metallic plate P1, they carry different values of kinetic energy. And when P2 was made negative, like we said, the photoelectrons decreased, reaching P2 decreased. So what is happening? Electrons possessing or carrying lesser amount of kinetic energy, they are easily repelled by P2 and they do not reach P2. Whereas electrons carrying higher value of kinetic energy, they are still able to reach P2. So that is what we mean over here. So if P2 is given negative potential, current immediately decreases but does not become zero. Why? Because electrons or photoelectrons having more value of kinetic energy, they are still reaching plate P2 against the force of repulsion, still reaching. So this shows that photoelectrons have kinetic energy but of different values. So this is what we can conclude. And furthermore, on increasing negative potential of P2, now what we do is, P2 is already negative, we further go on increasing the negative potential of P2. We go on making it more and more negative with respect to P1. So what is seen is the current rapidly decreases and at a certain value of negative potential, it finally becomes zero. So this negative value of the potential of P2 at which photocurrent is zero is called stopping potential. So this is zero, mean potential difference between plate P1 and P2 is zero. So this is P2 is positive value. This on the right hand side of this vertical line, what we know is P2 is positive with respect to P1. So when positive potential of P2 is increased, there is no increase in the value of current, photocurrent, as you can see. But when P2 is made negative with respect to P1, photocurrent goes on decreasing as the graph depicts. And at a certain value of negative potential of P2 with respect to P1, of course, what is seen is that the photocurrent is zero. So this value of the negative potential of P2 with respect to P1 at which photocurrent becomes zero has a name. It is called stopping potential or cut-off potential. Very, very important for you all. Remember, this is denoted by a capital V with a naught, V naught. So the negative value, I repeat, of P2 with respect to P1 at which photocurrent becomes 0 is what is called your stopping potential, mind you. So this graph is, that is what the graph is telling us. Then since stopping potential stops the maximum energy electrons, so what is happening at the stopping potential? Let us revisit the graph. See, as P2 was made negative, more the photocurrent goes on decreasing, as you can see. So photoelectrons having more and having different values of kinetic energy, they are unable to reach the plate P2. So lesser value at this point, the electrons having least value of kinetic energy, they do not reach P2. Then at this value, what is happening? At this value, at stopping potential, the photoelectron having the maximum value of kinetic energy is also not able to reach the plate P2. That is what is happening at the stopping potential. Okay, so at the stopping potential, since stopping potential stops the maximum energy electron, so stopping potential is also a measure of maximum kinetic energy of the electrons. So stopping potential is E into V naught. This comes from the definition of electron volt, mind you. So the maximum kinetic energy, if Ek is the maximum value of kinetic energy carried by an electron, so Ek is equal to E into the stopping potential, mind you. A very, very important equation for you all. Now, something more is observed at the stopping potential. And what is that? At the stopping potential V naught, even if the intensity of light is increased, the photocurrent is not obtained. So what we had seen earlier is when the intensity of light is increased, okay, photocurrent increases. That is what we had seen. But what we are getting to see over here is at the stopping potential, at this value V naught of the potential of P2, V naught, where the photocurrent becomes 0, even if we increase the intensity of light, okay, that has been depicted in this graph. So at the stopping potential, even if we increase the intensity of light, thus at stopping potential there is no photocurrent seen. So at the stopping potential, even if the intensity of light is increased, the photocurrent is not obtained. Okay, whereas when the plate P2 is positive with respect to P1, you can see on increasing the intensity of light, the photocurrent has increased. Okay, on I was the initial intensity of light. You double the intensity of light, the photocurrent gets doubled, you can see. But at the stopping potential, we are talking about at this specific value. At the stopping potential, even if the intensity of light is increased, no photocurrent is obtained, which means the stopping potential, or so to say, the maximum value of kinetic energy possessed by electrons is not dependent on intensity of light. Or so to say, the kinetic energy carried by photoelectrons is not dependent on the intensity of light. Okay, stopping potential, mind you, is a measure of the maximum kinetic energy of electrons. So, stopping potential or maximum kinetic energy, or so to say kinetic energy in general, is not dependent on the intensity of light. Very, very important graph, very, very important observation. Next, very important observation is this. So if at the stopping potential, we tried increasing the intensity at the stopping potential, there was no photoelectrons, obtained. But at the stopping potential, if we increase the frequency, you can see from this graph over here, at the stopping potential, keeping the intensity of light fixed, okay, the intensity is fixed. So keeping the intensity fixed, at the stopping potential, we use a light of higher frequency. So when we use a light of higher frequency, what happens is at the stopping potential, photocurrent is re-established. This shows higher the frequency of incident light, higher will be the kinetic energy, or so to say, the kinetic energy or the maximum kinetic energy of photoelectrons is dependent on the frequency of incident light. You can see for light having frequency nu1, lower frequency nu2 is greater than nu1. So light having lower frequency nu1, stopping potential is here. But when we use light having higher frequency nu2, the stopping potential at this value, at V01 rather, okay, for light having higher frequency, there is photocurrent. This value of photocurrent, you can see this value of photocurrent. So photocurrent is re-established if we increase the frequency of light. So this means maximum value of kinetic energy, or so to say kinetic energy in general, of photoelectrons is dependent on the frequency of light used. A very, very important observation. Now furthermore, if using light of different frequencies, so we use light of different frequencies and a graph for every different frequency of light used, okay, the maximum value of kinetic energy or the stopping potential will be different. For every different frequency of light used, they will get different values of kinetic energy or different values of maximum kinetic energy for the photoelectrons, mind you. So if using light of different frequencies, a graph of maximum kinetic energy of photoelectrons and frequency of light be plotted. So we are plotting Ek and frequency of light. What we get is we get a straight line. We get this kind of a straight line. Okay, so what can we conclude? What can we conclude is, for a given metal plate, okay, we are using a given metal plate, the cathode, the negative plate, so to say, okay, or let me not say negative plate, let me say P1. This is the cathode, this is the metallic plate, remember, P1. So for a given metallic plate, there is a minimum value of frequency of light, so you can see. So different frequencies of light, we go on increasing the frequency, the maximum value of kinetic energy goes on increasing. You can make that out from here also. Higher the frequency, the maximum value of kinetic energy goes on increasing. The stopping potential will go on increasing. Okay, so frequency increases, the maximum value of kinetic energy also increases. Now, what was observed is, for a given metallic plate P1 or the cathode P1, there is a minimum value of frequency below which there is a minimum value of frequency of light, of course, okay, below which that metallic plate is not going to emit any photo current, and thereby there will be no photoelectron or photocurrent. It is not going to emit any photoelectron. So this minimum value of frequency of light for a given metallic plate is called threshold frequency or cutoff frequency. So for every metal, there is a minimum value of frequency of light above which that metallic plate will emit photoelectrons. But below this minimum value of frequency, that metallic plate will not emit any photoelectrons. So this minimum value of frequency is what is called, for a given metallic plate, remember, is what is called threshold frequency or cutoff frequency nu0. So to say, for a given metallic plate, if we use light having frequency greater than the threshold frequency for that metallic plate, then that metallic plate is going to give us photocurrent. But for that metallic plate, if we use a light having frequency lesser than the threshold frequency for that metal, then we will not get any photocurrent, remember. So every metal has its value of threshold frequency or cutoff frequency, remember. Now I have drawn that graph of the maximum kinetic energy versus frequency again, and this is the straight line that we get. All right. Now if we are to get an equation of this straight line, okay, now we know, you've done this before, you must have done this in the mathematics. So the general equation of a straight line is y is mx plus c, where m is the slope of the straight line and c is the y-intercept. This value is what is called c, or the y-intercept. So this is the positive intercept, positive x-axis, sorry, positive y-axis. Now comparing it, comparing the equation of this straight line with this straight line general form, we get to see that the y is ek over here, x is nu over here, and let us say a is the slope of this straight line and b is the y-intercept, but this is the negative intercept. This is on the negative y-axis side below the origin. So therefore we have the straight line equation is ek is equal to a nu minus b. So this is the equation of this straight line. All right. Okay. So do keep this in mind, this equation. This is our equation number 2. All right. Now, what was further observed is that, if we use different metals, say we use two metallic plates 1 and 2, and we plot the graph of Ek versus nu, the same graph, this very graph for two different metals, we see that the straight lines that we get, they are parallel to each other. So to say, what can we conclude from this observation for different metallic plates is that the slope is a constant. Since they are parallel to each other, we get to know that A is a constant, the slope A is a constant, whereas B, the intercept, this is for the first plate, the y-intercept, and this for the second plate. So the intercept B depends on the material of the cathode plate P1 or the metallic plate P1. That is what is understood, because the value of the intercept is different, the value of B is different. Okay, so B depends on the metallic plate and A is a constant, the slope is a constant. So these are the different observations that were seen by, Henrik Hertz and Philip Lenard when they performed the photoelectric effect experiment. All right. Now, those were the different conclusions drawn. Okay, different observations are different conclusions drawn, and thereby we have the laws of photoelectric emission. Okay, it's the same thing that we have, discussed so far. So the rate of emission of photoelectrons from a metallic plate is directly proportional to intensity of incident light. So this is the first thing that we learnt. Okay, that is the photoelectric current is directly proportional to intensity of incident light. That is the first law. Then we have the maximum kinetic energy of photoelectrons is independent of the intensity of incident light. We learnt this also. The maximum kinetic energy of photoelectrons increases linearly with increase in frequency of light. Okay, that is shown by this graph. V0, the stopping potential, represents maximum value of kinetic energy. So as the frequency increases, the maximum value of kinetic energy increases, or so to say, the negative value of the potential, that is the stopping potential, goes on increasing. So frequency is dependent on, the maximum kinetic energy of photoelectrons is dependent on frequency of light, but is independent of intensity of light. Furthermore, no photoelectrons emitted from a metallic plate below a certain lowest value of frequency called threshold frequency. So below the threshold frequency, if I'm to show you the graph one more time, so you can see the graph of Ek versus nu. So below the threshold frequency, there is no photocurrent. No kinetic energy means no photocurrent. Okay, so that is the fourth thing. And no time lag. There is no time lag between light being incident on the metallic plate and photoelectrons being emitted from it. So the moment light is incident, on the metallic plate, simultaneously at that very moment photoelectron starts getting emitted from the metallic plate, remember. So to say, there is no time lag between light being incident and photoelectrons being emitted. So these are the laws of photoelectric emission. You want to be asked directly, about the laws of photoelectric emission. Even if you are asked, at the most you will be asked about 2 points. Okay, you can write any of the different conclusions. These are actually the different conclusions drawn from the observations made. All right, now let us briefly look at why the wave theory failed to prove photoelectric effect. Now, according to wave theory, as the intensity of light increases, what happens is the energy carried by the wave increases. So when we increase the intensity of light, when we make the light brighter, what happens is the energy carried by wave increases according to wave theory. So wave is like this. So when we increase its intensity, so we are increasing the amplitude of the wave, so to say. Okay, so the energy carried by the wave increases, so to say. And thereby what should happen is the energy of photoelectrons should have been dependent on intensity of light. You have an electron over here. So when an electron is being hit by a wave having a larger amplitude, it should be displaced, to a greater distance. So to say, the photoelectrons being emitted from the metallic plate should have been dependent on the energy carried by the wave, or so to say, on the intensity of light. But that was not true. That was not observed, something that was not observed, because we saw that the energy or the kinetic energy of photoelectrons, maximum kinetic energy of photoelectrons, is independent of intensity of light. Okay, because at the stopping potential on increasing intensity of light, there was no photocurrent obtained. Okay, so therefore wave theory failed to prove this. Another thing, according to wave theory, light of any frequency. So according to wave theory, we could have used light of any frequency, however low of frequency it be, but if it had a given value of intensity, a definite intensity, quite intense light we use, but of a lower frequency. Now, according to wave theory, that light having lower frequency but high intensity should have also been able to eject electrons from metal surfaces. Okay, because higher the intensity, more is the amplitude of the wave, remember. Okay, so energy carried by the wave does not depend on frequency, but depends on the intensity of light according to wave theory. But this was, the second point was also, this was also not true. It was found that, below a certain lower frequency, even if we, below threshold frequency, even if we go on increasing the intensity, there was no photocurrent observed, remember. Okay, so wave theory failed to prove this also. So after the failure of the wave theory to prove photoelectric effect, like we've said earlier, Einstein used Planck's quantum theory to explain photoelectric effect. Now, what did quantum theory say? Quantum theory says that, light travels as definite packets of energy called photons, and each photon carry an energy h nu. So, light or photons are coming and striking the metallic plate. So you have the metallic plate. The metallic plate is made up of atoms, number of atoms like this, and there are, since it is a metal, there are many free electrons also. So photons are coming and hitting free electrons, hitting valence electrons, hitting electrons inside the inner orbits. Okay, so the energy carried by the photon, what is it being used for? The energy carried by the photon is used up to take the electrons out of the metallic plate. So if this is the boundary of the metallic plate, this is the surface of the metallic plate, so energy of the photon is used up to take the electron out of the metallic plate, and then whatever amount of energy is left, that is given as the kinetic energy. And before that, you need to understand something called work function. Any metallic plate will have something called its value of work function. Different metallic plates will have different values of work function. And what is work function? It is the least value of energy required to emit an electron from the metallic plate. So the least value of energy that is required to take an electron out of the metallic plate is what is called the work function of the metal. So work function is a characteristic of a metallic plate, remember. Okay, now out of these different electrons, free electrons, valence electrons, and electrons in the inner orbits, the photon will have to spend least amount of energy to take out free electrons from the metallic plate. So it takes out, so to say, least amount of energy is required to take out free electrons from the metallic plate. So work function is this. The work function is the energy required to take out the free electron from the metallic plate, so to say. Because only for a free electron, least amount of energy is to be spent to take it out of the metallic plate. Whereas for these electrons, what happens is you have to overcome, the energy is spent to overcome the pull of the nucleus. So more energy you have to spend to take out these electrons from the metallic plate. All right. So the energy of a photon, okay, so we are talking about a free electron specifically over here. So for a free electron, least amount of energy or work function amount of energy is required to take it out of the metallic plate, and it is this electron which possesses the maximum kinetic energy, because then after whatever energy is spent out of this amount of energy, whatever is spent, okay, that is the value of maximum kinetic energy that it possesses. Okay, so you can see from here also these electrons are also emitted, but more amount of energy is required to take this out of the metallic plate compared to free electron. So this will possess lesser amount of energy. If it is this electron that is to be taken out of the metallic plate, you require the highest amount of energy or more amount of energy, to take this out of the surface of the metal, and thereby this will possess the least amount of energy, kinetic energy. So you can see different electrons coming out of the metallic plate, they possess different amount of energy also. Alright, so now talking about work function, the least amount of energy required, in which case the electron is going to carry maximum kinetic energy. So the energy of the photon is used up to do two things. Okay, in all these cases also the energy of the photon is used up to do two things. One is to take the electron out of the metallic plate, and then to provide the remaining amount of energy is used up to provide the kinetic energy. So energy of the photon is used up to do work function plus maximum kinetic energy in case of this electron, free electron. Used up to do two things in general, remember. Okay, to take the electron out of the metallic plate and then to provide kinetic energy. So in case of maximum, this is only in case of maximum kinetic energy, mind you. So in case of maximum kinetic energy possessing electron, photon energy is W plus Ek, or Ek is h nu minus work function. Alright, now if we compare this equation number 3 to our equation number 2, which is this, Ek is A nu minus B. Where is that equation? Here. Okay, that we get from this straight line. So comparing it to this equation, we get to see that the slope of the straight line is equal to the Planck's constant. The slope, A was the slope of the straight line, so slope of the straight line is equal to Planck's constant. And we had already seen that A is supposed to be a constant in this graph. So A is a constant, B depends on material of the cathode plate, that is what we had observed. Okay, that is what Frank and Leonard had observed, Hertz and Leonard had observed. So A is a constant, and we get to see that A actually is equal to Planck's constant. A actually is equal to Planck's constant, and B was dependent on the metallic plate. So B is, we can see comparing these two equations, B is work function, which depends of course on the material of the cathode plate, or so to say depends on the metallic plate. Okay. Alright, so see, this is how, Einstein is explaining the different observations of, this is what was observed by Hendrik Hertz and Philip Leonard's experiment. This is what we had got. Okay, and Einstein, this is what we get from Einstein's explanation. And Einstein is being able to, very well explain photoelectric emission. Now, from this equation, from this equation, Ek is h nu minus W, if nu is nu naught, nu is equal to nu naught, that is the threshold frequency, then the value of maximum kinetic energy is 0. You can see from this graph. Okay, we've already seen if nu is nu naught, the threshold frequency, then Ek is 0 at this value from this graph. So substituting that, Ek is 0, so substituting that, these values, we get to see W is equal to h into nu naught. The work function is, so to say, is equal to Planck's constant into the threshold frequency, remember that. So substituting the value of work function in this equation, we get to see Ek is h nu minus h nu naught, taking h common, we get this, and I forgot to write Ek over here, maximum value of kinetic energy. Now, if Vmax is the maximum velocity of the electrons, so whichever electron has maximum velocity Vmax has maximum kinetic energy. So maximum kinetic energy is, in that case, half m Vmax squared. So this equation can be written as half m Vmax squared instead of Ek is h nu minus nu naught. So this is what is called your Einstein's photoelectric equation. So this is your Einstein's photoelectric equation, which can also be written, okay, this is Einstein's photoelectric equation, which can also be written this way, because Ek is E into V naught. We have seen stopping potential is a measure of maximum kinetic energy. So E into V naught is Ek. So Ek is half m Vmax squared, which is E into V naught. So rearranging and taking E to the right hand side, we get V naught is H by E into nu minus nu naught, or we get this. And when we plot a graph of V naught versus nu, stopping potential versus frequency, we get this graph, which is the same as actually this graph, because EK is, here we have plotted EV naught because EK is EV naught. So EV naught versus frequency, this is V naught only versus frequency. The graph is the same. Only thing is, in this case, the slope we are getting to be H. After Einstein's explanation, the slope is H, and here the slope will be H by E, because you can see from this equation over here. All right, and when you compare it with this equation, y is mx plus c. So m is H by E over here, and c is minus H by E nu naught. So this value is H by E nu naught. So the intercept, since it is negative, okay, the intercept is H by E nu naught. So from here, what can we do? What we can get is, we can determine Planck's constant, the value of Planck's constant, from this equation actually, or from the slope. So the slope of V naught versus nu graph is H by E, we've seen. So H by E is tan of this angle theta. Okay, slope is given by tan theta, which is equal to, from, if that is theta, this is theta. So tan theta is perpendicular by base, so BC by AC. So H is, you can see from here, H is BC by AC into E. Now we can measure BC, we can measure AC, we can measure BC, we can measure AC, and we know the value of the electronic charge, okay, the electron, so to say, which is 1.6 into 10 to the minus 19 coulomb. So substituting those values, we can determine the value of H. All right, and we get to see H is 6.626 into 10 to the power minus 34 joule second. Sometimes you get asked this question: what is the value of the slope of V naught versus nu graph? I have seen one mark question come this, okay, V naught versus nu, whereas EV naught versus nu or EK versus nu, the slope of this straight line is H, that of V naught versus nu graph is H by E. So this is all, everything about photoelectric effect. Thank you.